Okay, so from yesterday, uh, our what was the main thing that we spent time on? With one formula, and that was the quantity of heat that's measured in joules equals the mass of that object times its specific heat times a temperature range. Okay. We also spent time with specific, molar heat of fusions and molar heat of vaporizations and how to convert them from kilojoules per mole into joules per gram. Now, the main idea behind that is when we are measuring heat, we want that to be labeled in one of two variables, and that is what? Joules or kilojoules, okay? So I've got some more information to write down on this one because this is a long problem in a process of what some of these, whether it's substances or elements, go through and how much heat is required to go have that go through its separate phase changes. We'll go into that in a few minutes. So, like I said, you can always go back to this video and write down or hit pause and then come back to it. Time. Oh, that's right. None of you are leaving. So for track. So time is not of the essence. So it's not quite as critical as what I thought it would have been. Okay. So like I said, there's a couple more things I need to write in there. Okay. Okay. So whether you want time to write this down, or should we go ahead and continue right now? Which do you prefer? Because yes, the bottom one is quite an extensive problem, but we'll walk you through it. That's sure. That's what I just asked. Yes. I need to talk to one of the bus drivers too, but I see they're not out there at this time. So regardless, what do those two problems have in common? Look at the first sentence. Well, both of them do. So a couple things. They have a temperature range. Yeah. So what the bottom one is referring to is when we're looking at aluminum, if we're starting at 210 degrees Celsius and we're going to vaporize that substance, it's going to go through a lot of phase changes. Okay. But in the top problem, something, let's see here, that is, okay, so copper. One of the things that maybe an engineer like yourself, okay, maybe yes, maybe no, what is one of the problems with a lot of, not tar roads, but asphalt roads right now going over a culvert? Why is there a depression in there? Nope, it's not necessarily washed out. And, well, it can be, but I think it's more so an upheaval from the frost on both sides of that culvert. So it kind of puts a little smile in the road. So it creates a couple bumps. But on a similar fashion, if you were, let's say, designing a bridge, especially if the temperature range is quite extreme. Well, I wouldn't say extreme, but it's cold in the winter and warm in the summer. What is it that you have to allow for that bridge to be able to do? It has to be able to expand and contract. Because one of the problems that we had talked about on that very first day is what's one of the biggest problems with concrete in the summertime? When it gets hot, it's buckling, because what is it that makes the concrete more durable or stronger, if you want to call it that? Well, I know it does, but that's not a problem. But when it expands, there's something in the concrete. What did we call that? It's kind of like a grid system. We said kind of like the tile floor. It's something in the concrete. It's a metal. It's a very common term. What? The rebar inside of there. So you almost have to allow for that type of expansion in a bridge, because if you're looking at a span over a waterway, you're going to have to allow for that to expand between the two so it doesn't collapse, okay? So it doesn't push against your uprights, and you have to allow for contraction and it doesn't fall off of the uprights, okay? And I'm just using that as an example. Obviously, I'm not a mechanical or civil engineer, but that's something that they would constantly have to deal with. So the idea of understanding this would be, I would say, pretty important. Okay, so the difference between these two is, again, this is quite a vast temperature range. This top one is just saying, well, if we had copper at 110 degrees centigrade, how much heat would require to raise it to its melting point? So you don't have enough information to see all the different phases and how much energy that would take, unlike you do with this bottom problem, okay? Some of you are maybe looking, I have no idea what's going on right now, and that's probably the case because we haven't taught you this yet, okay? How do you know what a basketball play is until you go through it? How do you know what a new piece of music is going to be like until you go through it? You don't. That's why in this case, all right, there's a specific formula that we could use to aid with that, because it's looking for heat, and what variable would that be? Q. So a quantity of heat, okay, because that's what it's asking for. So this quantity of heat will equal, what else do we have in this problem? So we've got a mass. Yeah, we do have a temperature, that's true. What else do we have? And right, because that's what this is referring to. So how do we account for that temperature change? You said it's what minus what? Okay, so which one of these is the final temperature? So we're going to subtract what from 1085? Okay, so what we can determine here is Q equals our mass, which is 7710 times what? Usually we have a setup here, but we're kind of